Okay, so hello everyone. Thank you, Jess, for the introductions. My name is Dionysios Anemogiannis. I work for SciCo Greece, and it's a great pleasure for me to welcome you all to today's event, which also happens to be the first public event for the WaterWise Hub, but also a great opportunity to introduce a great EU initiative. Today we have Climate Impetus as the honorary guest. It's a project that concluded 2 months ago, leaving a strong legacy by accelerating Europe's climate adaptation efforts through testing and implementing demonstrators that address climate risks in 7 different biogeographical sites in Europe and testing 15 different technical and nature-based solutions. The project has also developed adaptation pathways, digital tools, and knowledge resources that help regions design and implement effective resilience strategies in collaboration with local authorities, with researchers, and communities. Here to share key takeaways from the project's case studies and tools developed are Dr. Dionysios Nikolopoulos and Dr. Klio Monokrousou from the Urban Water Management and Hydroinformatics group of the National Technical University of Athens. We will be referring to it as NTUA today. Dr. Dionysios Nikolopoulos is a civil engineer, and he holds a PhD by NTUA specializing in resilience assessment of cyber-physical water systems and a master's degree in water resources science and technology. He has expertise in hydroinformatics, water resources management, hydrology, applied hydraulics, and GIS. Since 2014, he has participated as a researcher in 17 national and European research projects at NTUA. In 2022, he was honored with the Mülheim Water Award for innovative research on safe and secure drinking water supply. Dr. Klio Monokrousou is a civil engineer and senior researcher. She holds a PhD in civil engineering by DUTH and a master's in environmental technology by the Imperial College of London. She has nearly 20 years of experience in research and consulting, primarily focusing on water resources management, environmental and water policies, and sustainable urban planning. For more than 10 years, she has served as a research associate at the National Technical University of Athens in the Department of Water Resources and Environmental Engineering. And in parallel, she has over a decade of expertise supporting policy development at national and European levels and engaging the civil society on water management issues through her roles as the Water Resources Coordinator and the President of the environmental NGO Mediterranean SOS Network. And now that the introductions are over, I would like to hand over the microphone to our 2 speakers so that they can start with their presentation. Thank you so much.
Thank you for the very thorough presentation, Dionysios. Hello, everyone. We have the pleasure today to present you our findings from the recently concluded Impetus project. I will skip the details as Dionysios already told you about our project. I will only state again that what we did was huge because we developed solutions, adaptation solutions, and also implemented the pilot cases in 7 very different biogeographical regions, ranging from the Mediterranean region to the North Arctic. So today we will present you some solutions tailored for the East Attica region. This is a sub-regional unit of Attica, which is the province where the Greek capital Athens resides. So just a few details. The East Attica has nearly 500,000 inhabitants, and a significant portion of it is urban and built areas. But at the same time, there are some significant agricultural activities and large natural areas that unfortunately are degrading rapidly. Also, this region is home to various industrial activities, and here we have some major ports and also the Athens International Airport. Unfortunately, this big region has been facing some significant challenges. For the last at least 2 years, we have a long dry spell, and the research for the external water supply system has seen its water availability diminishing. Things are getting better now, but we do not know how long this will last. And at the same time, in the last years, we have several severe wildfires that have devastated the region. While there are multiple reasons for these wildfires, that also includes arson and the general unpreparedness state of the region, the high temperatures and the prolonged dry conditions that we have been experiencing in the last years have exacerbated this risk. So, of course, as engineers, we would like to tackle these two challenges. And for this reason, we would like to know what to anticipate in the future as far as climate and socioeconomic conditions are related. However, we can only speculate about future scenarios, and for this reason, we use the shared socioeconomic pathways scenarios. These are a set of narratives that describe the future development pathways for human society. These narratives can be turned into quantitative projections for land use, energy use, water use, and other activities using integrated assessment models that correspond to various related forces. The recent CMIP6 mission has prioritized 4 different narratives. You can see them in the figure on the right, in order to create model experiments in order later to produce climate and socioeconomic projections for a global scale. From this mission, we can get 3 narratives, SSP 1, 2, and 5, which are roughly comparable with the previous phase, CMIP5. And these were the scenarios that Impetus utilized in all of the analysis throughout. So, what does the future look like with these scenarios and narratives in mind? Specifically for the East Attica region, we can see that the mean annual temperature is expected to have a sharp increase, as evidenced by this graph. And comparing to the previous historical conditions, this increase can be as high as 3 to 4 degrees Celsius on the average annual level. Looking into the total annual precipitation, we can see now a decreasing trend comparing to the previous historical conditions. And by combining these two increased temperature and decreased precipitation trend, we can speculate that the conditions in the region will be very dry in the future. In this graph, you can see the average standardized precipitation of evapotranspiration index, or SPEI, for a 4-year window for the whole region. And you can see that in the near future, the conditions are projected to be from severe to extreme, even when compared to the exceptional prolonged drought of 1989 to 1993 that happened in the region. And as a result of this historical prolonged drought, we had an alarm state for the system, and this prompted various emergency implementations of new water infrastructure. So let's take a look also at the socioeconomic changes in the region based on these narratives. You can see that for the East Attica population, there are projected some mild to high trends. Generally, the Greek population is decreasing, but because this is in the province where the capital resides, due to urbanization, we will have maybe some population increase. And at the same time, the same narrative speculate that the economy will be better. Let's hope that this will be true. And these two together form a projection for increased water demand in the system. So, coupling this increased demand with the changing hydrometeorological conditions, we have the uncertainty of socioeconomic droughts lingering above the East Atticus region future. How can we tackle now this condition? Of course, we have many options to adapt to this changing climate. And at the larger scale, at centralized system scale, let's say, there are some proposals from the regional authorities and the water utility of the region, including the implementation of desalination plants, creating a new water infrastructure that connects Attica to a huge reservoir in the West Greece, reoperation of older groundwater wells that are nearby, and others. However, we can also have some local adaptation solutions that are tailored for the region. Examples include rainwater harvesting, sewer mining units, a controlled environment from an agricultural scheme, reclaimed water from tertiary wastewater treatment and reuse it for agricultural industry, and many other things. So we have many options, and at the same time, our budget, including time and costs, is limited, as with every other engineering problem. Thus, we are in dire need for decision support tools in order to support policymakers taking the necessary steps in the future. Of course, similar problems are common across all European geographical regions, and having this extra long introduction, now this is where Impetus steps in. Impetus created various decision support tools to foster this climate adaptation. Pivotal here was the strategic planning scheme of adaptation pathways. What are adaptation pathways? Adaptation pathways are a sequencing of options through time with various criteria in mind in order to tackle the climate risk as it emerges. By tackling the climate risk, it reduces the impacts in the region. You can think of pathways as the paths in the figure, where you can have the blue path with 2 interventions spread across the time horizon, or the yellow path with 3 or more interventions closer together, or the green path where you have some interventions later in time. NTUA's work here was to develop a toolset and a methodology for designing these paths. To this end, within Impetus, there have been some other background tools that supported this methodology. For example, NTUA created HIPS, which is a hotspot identification and prioritization service, in order to identify which regions have the most problems. KWR and other partners created a comprehensive indicator and metric framework in order to quantify the problems and challenges, and AUEP created schemes to evaluate the cost effectiveness and hidden risks of various interventions within pathways. The work we are going to present to you now is 2 tools and a robust framework for adaptation pathways design. The tools are called the Risk and Emerging Problems Inference Engine, or REPI for short, and the Dynamic Contingency Response Tool, or DCRT. Our framework begins with identifying what is the main challenge in the region and what are the suitable interventions to tackle it. So we identify the key systems, we identify the main climate hazards for these systems, we create an impact chain model in order to quantify risk. We have alarm thresholds to measure and monitor the risk as it progresses, and also we identify the suitable solution set. We feed all this regional data into REPI to have the quantification of risk, and we feed the intervention characteristics in DCRT in order to create an optimization scheme. Now, together, REPI and DCRT are coupled, and with feedback loops, we reach an optimized sequence of interventions that minimize risk and other criteria in the region. Let's go step by step now by first looking at what REPI essentially does. REPIE is an operationalization of the impact chain analysis. And what impact chain is a generic model, generic framework, where you have hazards, exposure, and vulnerability indicators that together have causal relations that produce the risk for a specific impact to be manifested in a region. In REPIE, each one of these elements, hazards, exposure, and vulnerabilities, is weighted. So you can have different hazards, like, for example, rainfall, temperature, the SPI index, or whatever. You weight them and you produce a hazard element. You can have then vulnerability elements, like, for example, what is the water demand per capita, how stressed is the national economy, how old is the water distribution network, for example. And again, with weights, you get a vulnerability element. And then you examine how much exposed are your systems to these hazards. And then we do the classic risk estimation that is based on hazards times vulnerabilities times exposure. For each one of these variables that I just described, users define alarm thresholds. We have 4 alarm thresholds in REPIE: low, medium, high, and critical threat levels. Users generally examine the historical records of these variables in the region and estimate these 4 threat levels. These 4 threat levels are used in order to normalize each variable, each indicator, into a common scale of 0 to 10. So we can use the risk equation to produce a risk level based again on the same scale from 0 to 10. So when you have projections for each variable, this may be climatic projections, for example, from Copernicus, or socioeconomic projections based on SSP narratives, you can quantify for each one of the variables how it is in the future, how it evolves as time goes by. Users utilize simple Excel templates in order to feed the REPIE with data. Users supply the variables with their names, their types, the weights in order to have the weighting factor between the same type variables to affect the respective dimension. Users also supply the thresholds per variable and also the data path. And we can have a single potential impact in a region, or maybe we can have multiple impacts per region, and also we can examine multiple key systems with their specific impact chains. We have a simple file structure in order to pass these inputs to REPIE. We just provide REPIE with a zipped file that has folders with the time series and the user input. Of course, the time series should be in a specific structure, like you see in this picture. And then REPIE runs a simulation of risk in the region and produces graphs like the one that you see here. So for each different scenario, for example, SSP1, SSP2, or SSP5, we have different risk curves. These risk curves can be produced by coupling single models for each scenario, I mean climate models, or even aggregate multiple climate models. For example, in our case that we will present you later on, we used these 3 SSP scenarios, but each one had 8 different models to evaluate the future climatic conditions. Essentially, when you take these risk curves, then you can use them in order to generate different pathways based on each scenario, or then aggregate these scenarios to a single risk level metric and create a single climate resilient pathway. The choice is upon the users. Let's move now to the DCRT. The concept here is very simple. You have this risk curve and you try to find interventions in order to minimize it. Of course, the ideal condition would be to minimize risk for climate impact in a region to the value of 0, but most of the time this is not easily attainable. What is best also is not only a matter of risk reduction. There are many other considerations. You can think of, for example, cost or social acceptance and other things. In the CRT, we have 5 different dimensions where we examine the intervention characteristics in order to optimize the pathways. The dimensions are effectiveness, cost, feasibility, the temporal dimension, and externalities. In effectiveness, we have, of course, the regional scale of implementation. For example, how many sewer mining units can be installed in a region, or what are the different phases of implementation of different solutions. And of course, what is the effect on vulnerability or exposure indicators. We make the assumption in this RT that the climate hazards cannot be, of course, changed by local adaptation solutions, so only vulnerability and exposure indicators are affected by the introduction of a measure in a region. For costs, we have CapEx and OpEx dimensions. For feasibility, we have the technological readiness level, the societal readiness level, and, of course, the order of some of the interventions. For temporal characteristics, we have introduced lifetime considerations, sell-by date and sell-by conditions. And also very important here is how much time intervention needs in order to take place. And for the externalities, finally, we have some co-benefits, for example, ecosystem services, and hidden risks for each intervention. For example, if we need materials that are not available in the region, or if it is energy intensive, for example. Again, users utilize spreadsheets in order to provide the input, again, in a structured way. So we have the idea of each solution, the name, the effect that have on an indicator, either a percentage or an absolute value. We have the lifetime column, the sell-by date column, or the sell-by condition. And finally, we have what we call a precedence matrix, which is a matrix that denotes a specific order if needs to be. For example, if we have phases of interventions and intervention A must take place strictly before intervention B, we can materialize it with this matrix. Or, for example, we have some known strategies in advance or preferences in the region. So again, we can specify in this matrix how the specific relation between interventions is expressed. This is very important because we can evaluate the validity of the pathway, and of course we can avoid some lock-ins. For example, if intervention C, D, and E are have a mutual exclusivity with intervention B, we can use this scheme to test our pathways. So now we move to optimization. We provide all this data into the algorithm, and then we need to find the best sequence. Here we have a challenge. We do not know in advance how many interventions will be considered in a specific pathway. It can be 2, it can be 3, it can be 20, or however many the algorithm deems necessary. So here a solution of the DCRT is a vector that describes the timing of implementation for each intervention that we have available. This timing could be 0, and this means that this intervention is not suitable, for example, in a specific solution. We use a genetic algorithm, here specifically we use the NSJ2 algorithm, in order to create the various solutions. Each generated sequence of interventions is checked for its validity, and the invalid sequences are discarded. When we reach a valid sequence of interventions, we pass it to the rapier, and based on this specific implementation, rapier recalculates risk and also some other criteria that I'm going to present you in a bit, and then checks how performant this solution was. Some solutions that are under a user-specified performance threshold are discarded. So, for the key 9, because we are talking about generic algorithms and risk and other criteria, you can already identify that this is a multi-objective problem. So we produce Pareto optimal solutions. Why we produce Pareto optimal solutions? Because each time a perfect or ideal solution is not only what is technologically available and minimizes risk, but maybe we can have various other barriers, for example, social barriers for acceptance, or its monetary value, the budget can be very high, or it cannot be feasible for different conditions, or it has many hidden risks and other things. Specifically, within DCRT optimization, we look at 6 different criteria. The first, of course, is the regional risk, and this is to be minimized. The second most important criteria is the total cost of a pathway. We also look at the technical and social feasibility. We also look at deviations of annual spending from budgets. We also look at social cost benefit and effectiveness. And finally, the accumulation of different risks of interventions in a pathway. These 6 criteria produce a multi-criteria Pareto front in 6 dimensions. And with a meta-analysis of the results, for example, with different user weights, we can create interesting pathway options. For example, one user can say that, okay, I only want the most effective pathway and I not care about the cost or everything. The algorithm can give you this best sequence. Or another user can say, okay, I want a balanced pathway between all 6 criteria. I give equal weights, and then from the Pareto front, I take one single pathway that is balanced across everything. Everything is customizable. Essentially, DCRT produces results given back to the user as spreadsheets. You can see a screenshot here, where we have on the left image the idea of the solution, the effectiveness in the columns in the various criteria. In the middle figure, you can see the spacing of interventions in time. And in the bottom right figure, you can see the final risk curves per pathway that are created. Essentially, the output is like this figure, where we have on the x-axis the time horizon, let's say from 2020 to 2100. With the red curve, we have the baseline risk of the region for a specific climate scenario. And then the blue line is the optimized risk curve by implementing the interventions that you see as dotted lines across the horizon. So for this specific example, we have 6 interventions that are planned. So what I just showed you as a concept has been unified into a decision support tool. The decision support tool is called Paths. It integrates these 2 modules, Replier and DCRT. It is available online. You can check it if you want. It's hosted on our server. And even though Impetus has finished, Paths is being continuously updated. We have another EU Horizon project, Recreate, for which we use it. And soon will be updated with even more capabilities. Let's move to the eStatica case study, just to present to you how the whole workflow looks like. So here we have created an impact chain for socioeconomic droughts. So we have the hazards of rainfall, temperature, HPI, average temperature in summer months, days with high temperature, and others for the hazard. For the vulnerability, we have the dependency of the system to the central water supply, and of course to the groundwater local sources. And the exposure elements are the population, the industry, and the agricultural sector. Therapy produces these three curves for three scenarios. And here specifically, we have used the CMCC ESM2 Italian climate model for the climate projections. As you can see, the risk of socioeconomic drought in the region is very high. And in SSP5 scenario, it reaches even 10, so a very extreme condition. We have 6 different interventions identified suitable to combat the socioeconomic drought challenge. These are sewer mining units, rainwater harvesting schemes, controlled environment agriculture, reclaimed water from waste water treatment plants, desalination units, and informational campaigns and policies. Each of these interventions affects a different part of the vulnerabilities and has their own characteristics of time to implementation, social cost benefits, and other things which would not have the time now to present. And DCRT identifies 181 different Pareto solutions using these interventions. DCRT always and rather early opts for the informational campaigns and policy and the reclaimed water, the use of wastewater effluents specifically. Almost always opts for sewer mining units and desalination, and less frequently selects the rainwater harvesting schemes because it is considered ineffective when you have long dry periods. You can see a table on the right, which has the selection probability of each one of the intervention and the average year to be implemented. And you can see the Pareto front with the total cost and the effectiveness on the x-axis. These are, for example, the figures that are being produced for different pathways. Pathways 1 is the largest risk reduction. So you can see how the algorithm selects interventions to minimize risk. Pathway 2 is the pathway that has the least cost. And as you see, here it allows the system to have a risk up to level 5, and then it should take actions. Then we have other pathways, like, for example, the elbow point or the equal weights pathway. And just to give you an example of what happens in each one of them, for example, in pathway 1, here we favor desalination units and wastewater treatment effluent reuse. This is the most effective one. The least cost delays the interventions and omits the desalination unit because it's very expensive. The elbow point pathway has early implementation of some interventions and delays desalination due to cost, and the equally weighted pathway omits desalination but introduces more of the other interventions. We can do the same thing for other scenarios, like scenario 2 or scenario 1. I will spare you the time, because we are reaching the 40-minute mark. Just some remarks. These methodologies that we presented and the results were discussed in depth with the local stakeholders. We have validated that these pathways that we produce are within expectations. Specifically, the most effective pathway has selected the interventions in the order that are preferable within the regional authorities and the water utility. And this is probably something that will happen in the future. And within Impetus, we have also tested this methodology in a second regional case study, which is the Zemgali region in Latvia. Again, the results from the implementation were discussed with local stakeholders, and these have been deemed as successful. Now, a specific remark here is that these tools aim to be very generalizable, so you can take them and implement them in another problem, for example, not water droughts, but the energy sector. So the focus here is to be replicable with a bird's eye view. So that said, if we couple these tools with more detailed models, you can have a more in-depth analysis. So without being confined with a single risk evaluation, but with tailored metrics, for example, for a water system. This is exactly what we do in the frame of the Recreate project, where we have transferred this know-how. And instead of a risk estimation, we produce evaluations on specific indicators. So exactly how much reliable is the system, exactly how much a pathway costs, and other things. Stay tuned for the future of paths. And without further ado, let's give the floor to Klio to go from this general strategic scheme to the actual implementation on the ground for the sewer mining units. The floor is yours.
Thank you, Dionysios, and thank you for this presentation of the Impetus project. I will move on now with the more concrete solutions that we have developed on the ground within the project, coupled with digital twins that form a more integrated climate adaptation solution for the case of Attica. So I will just have a short overview of the region that we have focused on, which is the East Attica region, which is based on agricultural activities and is currently facing a rapid urbanization that alters the landscape and creates significant pressures on water resources. And of course, along with inadequate water infrastructure and urban expansion, this threatens the sustainability of the region and emphasizes the needs for more balanced development and conservation efforts. So what we did in the Impetus project in all these 7 regions, but also in East Attica, is to adapt to develop, implement, and test these adaptation solutions to become a landmark, a pilot, for being transferred to other regions as part of a more integrated climate resilience strategy. So what we did first as an initial step was to engage the stakeholders and share our views and concerns about the area, and we mapped and identified the potential interested parties. We created a registry of stakeholders, and we designed and implemented a very dedicated engagement roadmap that included a survey campaign from the very early stages of the project, 4 regional workshop events that engaged all the involved regional and also local parties, as well as business, water utilities, the industry, the academia, etc. And we created 2 annual newsletters, 3 videos with project results, regular posts, and of course dedicated technical meetings in the sites with regional and local actors. So I will give you some more details about
sorry,
2 of our...
Klio. We see the very first slide only.
Ah, okay. Now?
No.
Can you go on? So on the screen we can see, I suppose just like the PowerPoint as it would be on your desktop. So can you go from the beginning? Yeah, if you click that.
Now you can see?
Not yet, no.
Maybe you have two screens.
Maybe.
If you have 2 screens, maybe you are sharing the other one.
What about now?
No.
I will stop sharing and maybe start again.
There we go. Perfect.
Okay.
Thank you.
So, okay. So this was about the engagement of the stakeholders and the shared views and concerns that we have developed. And now I will move on to the implemented solutions that of the Impetus project, mainly the sewer mining, water reuse system, and which is coupled with digital twins and advanced visualization tools. So first, starting with sewer mining digital technology as climate adaptation solutions. This is practically a water reuse solutions, a decentralized solution that extracts wastewater directly from the local sewage network, which is located underneath the place of demand. You can see in the pictures the container, which is the system that treats wastewater in a compact unit through the MBR and UV technology and produces high quality water which is suitable for irrigation of green areas, of groundwater recharge and other urban uses like street washing or fire protection. And the main idea of this technology is that instead of treating water only in wastewater treatment plants and transfer them back to the city, we practically explore the possibility of moving the treatment closer to the point of demand. And this concept is also a decentralized, autonomous, circular economy solutions that transforms waste into a valuable resource. Let's have a look at the process here. We have two pumps, a small pumping station that works alternately and pump wastewater from the network at about 4 meter depth. And the raw sewage is then moved in a buffer tank and then to the main container with the MBR technology. Also, biological treatment is taking place, and finally UV disinfection so that it is suitable for the uses that I described. This unit in particular has a capacity of about 24 cubic meters per day, but it is totally flexible in terms of capacity as it can be adjusted according to the water needs of its park or according to the needs of a season. Here we can see some results from monitoring of the system and from the sampling that has been done in a regular base in the startup of the unit, but also during the steady state period. And we can see in green dots two of the parameters with that COD here, in particular in BOD, that completely meet all the national and international criteria for unlimited irrigation and urban use. This system, we have been working on it in different projects for more than 6 years, and we can see that it is efficient in treatment, but also stable in operation. So this is something that can be reliable, and with this system we can use the reclaimed water to create a series of gardens around the technology and use this water for irrigation, create additional green and also irrigate the existing parks, of course. And apart from this, we have moved on. Here we can see some photos from our two pilots in the urban green parks of Monokrousou, but also in the urban nursery of the city of Athens. And in the second application, we can also see a pergola with photovoltaic panels on top, where we have we have extended the solution to be energy efficient and have an autonomy of about 90% for the entire facility. So we have also created a bioclimatic environment with shadows for the visitors, apart from getting the solar energy for the operation of the unit. So we have done water recycling, energy efficiency, and now we have also created the surrounding environment to be of natural materials with a reduced footprint in accordance with the circular economy principles. So we have designed as you can see in the pictures, an amphitheater to be hosting visitors and interested people to be created of straw and clay, and inside there are recycled glass bottles, so that it's made of natural materials, and the fence is made from wooden boards of all shattered. There is also a small pond with recycled water of compacted clay and stones. And also the pathways are paved with stones from the local area, and the surfaces are finished with lime plaster so that CO2 is absorbed by the atmosphere over time. So the main idea of this construction is that we can use natural materials from the area that when are dismantled, they do not produce construction waste, and instead they can naturally return to the environment or be reused again for reconstructing other facilities. So this entire area is also transformed to be an education and awareness center with several events and training workshops with schools and students and other interested parties, both from the local area, but also from a higher level of governance, so that they can visit the amphitheater and have a guided tour in the facilities of the water reuse system. There is also an open-air exhibition that explains the different steps of the processes of the treatment, and of course the gardens that are irrigated by recycled water. Now moving on to our second solution, which is very much connected to the first one that I just described, is the digital twin platform, which is practically the virtual system of the physical system that can be replicated and be remotely monitored. So we have these advanced software systems that can help us monitor and visualize at the same time the operation of these systems. As you can see in the picture, we can navigate in the digital system and see the tanks along with the sensors in the red dots, and we can click on them and see the real-time value of its parameter according to our needs. And of course, we can get historical data of this parameter, see the trends, and realize how the unit operates and what are the limits of the different values. And this is, of course, to provide insight to the end users and be able to train them, and so that they can replicate, scale up, or adapt these solutions to other needs and other conditions of their region. So in the Attica region, we have already developed through the Impetus project a dynamic tool, a dynamic platform. You can visit it, and it's operational with this virtual representation of the both of distributed solutions like the sewer mining unit, but we also have geospatial services that have been developed within Impetus. And this uses real-time data, as I said, and produces advanced analytics and simulation models to mirror the physical systems and to monitor them, so that we can assess the performance and create and take more informed decisions. Now, if we can summarize the benefits of the Attica Digital Twin, we can have, of course, the very beneficial aspect of remotely monitoring and controlling the system 24/7. It's the entire platform is a one-stop shop that it's completely expandable, and it can identify these solutions in the particular area and can be including more visualized systems that are important for monitoring, like nature-based solutions, rainwater harvesting applications, or other desalination units like Dionysios described before, any other decentralized or non or central solution that is being producing data flows. And this is, of course, also a training and engagement tools for end users and policymakers so that they can take benefit of it. As I said, it is designed to be scalable and transferable, and it's useful for decision making and for maturing these innovative applications. Some examples here: we can visualize the operation, as I said. We can enable remote monitoring and prevent any unexpected event, or train end users that can, for example, a municipality that can hand over this technology after a project finishes. They can be easily trained through this visualized PLC system that we can see on the right. And if I can sum up some of the challenges that we came across during the project, of course, the regulatory framework has certain barriers for this innovative solution. So we had to struggle with these permitting processes and create a roadmap to be compliant with applicable regulations. Of course, another aspect is the social acceptance and the collaboration with the authorities and the different departments when implementing such solutions, and this has to begin early. We have to be building trust with these people that work in the local authorities, and provide guidance and information to the social communities, and can increase the acceptance of these solutions. Of course, it's important to have an uninterrupted operation of the systems, both the physical and the digital, so that it can be reliable and it can facilitate the seamless operation and prevention of any unexpected event. And to ensure accessibility of the system, we need to have access and get this data accessible to the end users, to the researcher, and to policymakers. And this can promote, of course, the transparency of the projects and highlight more the impacts. So next steps is to further engage and demonstrate these concrete results to stakeholders, as we will be implementing in other projects like Theseus, for example, other sewer mining facilities, to be doing interactive workshops with the local authorities, promote the videos, and also have tours, and engage other potential end users to be interested for implementing such technologies in their areas, and of course engage with other parties and collaborations for the promotion of topics related to this, but also to reuse, circular economy, and climate change adaptation. So I will stop here, and we are available for questions and discussion.
Thank you very much, Klio. Thank you, Dionysios. Thank you for your presentations. They were very interesting and very thorough introduction and comprehensive introduction to climate impetus. I'm sure we have a lot of questions. I would maybe suggest that we extend the webinar for like 5 more minutes just to get some questions answered, if that's okay with everyone. Perfect. So I think we have already one question in the chat. Let me have a quick read through. I think, Dionysios, you have also already provided a short answer. The question is basically asking, how do you take into account irreversibility of some interventions which spanned in time may lead to controversial decisions, for example, costly infrastructure investments. Any ideas?
This is a very interesting question, and this is what we have been thinking also when we were developing the tools. How can we avoid such things? So there is this thing that you need to have low regret options selected most of the time. So you make a decision on something that is very, for example, costly or energy intensive or not very good for a community. It has some social barriers. How will you avoid this thing being introduced in your design? So what we can do is that when we pass the information of each intervention into the DCRT tool, we have a specific field for the parameters, which reads as hidden risks. Now, what exactly is this thing? This is an evaluation of multiple KPIs. I didn't present this because it would take like 10 more minutes, but essentially when we examine an intervention, we look at things besides its cost and its implementation time and technical feasibility. We will look if it needs materials that are not present in an area. We examine if it introduces inequalities in a region, and at least 10 other KPIs. These were developed by AUAB in Impetus project, this evaluation. And it is tailored for each specific region because it uses data in a NUTS2 spatial dimension. So we have the different KPIs, and if an intervention can be risky, it has a high hidden risk score. When you optimize the pathways, if you select this criterion to be part of the optimization, the algorithm tries to avoid it or balance it out with other interventions that are of lower risk, so of lower regret, let's say, if being introduced into the pathway. Essentially, it will be part of some pathways. If we do a multi-objective Pareto optimization and generate, let's say, 100 different solutions that are valid, users can skip the solutions where this is part of.
Perfect. Let me just mention that Dionysios has also shared the link to the Paths tool and platform. So you can find this in the chat. Also, another opportunity for anyone interested to know more about this decision-making tool. There will be another opportunity to potentially discuss about this in the next webinar session planned by our webinar series, which will focus on Recreate, the other EU project mentioned in the presentation. So keep an eye on that because we will be posting more information on that soon. Any other question? One last question. Maybe we have a little bit of time to answer if anyone has any pressing questions. Diana?
Yes, well, thank you for the excellent presentation. We are from Project Arsinoi. We had a common project meeting in Utrecht, in Netherlands. KWR were hosting. I was following this presentation. It's a great tool. It's similar to what we have developed in Arsinoi. I hope you will be able to follow our webinar on April 1st. My question is, you mentioned cost effectiveness as one of the criteria. How did you estimate capital expenditures and operational expenditures, considering that it is an environmental asset, actually? And also, you actually, in your overall methodology, you actually use multi-objective optimization with multi-criteria decision analysis as a follow-up. It is a very effective tool, but on the other hand, what you rank may disqualify some of the pathways. If you use only multi-criteria decision making, maybe you can incorporate all the pathways, adaptation pathways in one strategy, but just suggest the schedule of implementation based on multiple criteria. So the second question is, what would you say about the effectiveness of this methodology of multi-objective optimization, followed up by multi-criteria decision analysis in projects where a participatory approach is very important? Thank you.
Thank you. So for the first aspect of your question, what we have developed in Impetus is an evaluation database that uses KPIs from Eurostat that relate different aspects of life with the ecosystem services that can be provided by the interventions. So for each intervention, we estimate a CapEx and an OpEx based on a desk study or speaking with the authorities or speaking with or finding the information on previous case studies, as is, for example, the case with the sewer mining units, which we have made studies in the past, and we know, for example, which is the average cost of installation. We have already two pilots. We had already two pilots, for example, in Athens. We had the third one in Impetus, so we knew, for example, how costly it would be in terms of CapEx and OpEx. Then, using the evaluations database, we see at what other ecosystem services this type of intervention could provide to the community. For example, the ecosystem services of a sewer mining unit could be that it can irrigate an nearby park, and this was evaluated at using this valuation database at a specific amount of let's say, environmental benefit. Okay. Then we compare the average cost of installing, I don't remember exactly now, but I think 70 or 50 was the number of these units with their ecosystem service. And then we compared the other interventions with the same CapEx, with their own CapEx and with their own ecosystem services evaluation that they would be providing. And this is how we got the CA, the cost effectiveness assessment number for each one of these. This later is integrated as the co-benefit value in the tool. So each one of the interventions has its own co-benefit score. And in some pathways, this is to be optimized, and then you get the best mix of interventions in time to maximize the co-benefit against, for example, the overall risk reduction or overall cost. And now this brings me to the second part of your question. Essentially, what we do is that we only generate the solutions with the algorithm. So the algorithm generates, for example, 100 or more solutions that are between them not easily comparable, because each one of these is better in one criterion than the other pathways, and less, and let's say worse in other criteria. But all of the solutions among them are not dominating, so you cannot select a specific one from this set. All are equally valid and equally good when you examine from a bird's eye view the problem. The process of identifying which one of these is to be finally used in a region is a matter of speaking with stakeholders and seeing what exactly are their preferences, what exactly are the challenges in the region, and what solution from these is better for the region. So if you do an engagement process with various stakeholders and they say, oh no, just want the most performant, the answer is easy. You see which solution has the best value in criterion 1 and you select it. If the region has limited budget, or this budget is spread across multiple years, then again, you can see which pathways are within the budget, you discard the rest, and from then, from the new set, you can also specify which is more tailored to the region. Again, you just create the answers, and you have to engage with everyone in the region in a participatory analysis in order to reach a final conclusion. We just speculated that 4 here would be important for a region, and we showed you them. And also these 4 were discussed with the stakeholders within Impetus. But the tool can support policy making, because you can go to the regional authorities, say, okay, I have optimized the solutions for your problem. This is the list. Now we can sit down and reduce this list to a more manageable set of solutions. Let's say, okay, what is our budget? Our budget is above this X amount of money. Okay, half of the solutions are above this budget, so we discard them. And now we can see, are there solutions that are difficult to be implemented here? Is there feasibility or their social acceptance low? We discard them. Should we reach a specific value of protection from the climate change hazards? Yes, okay, so we discard the solutions that are less performant. And you get 3 or 4 solutions to be discussed with everyone. So essentially, after creating the solutions, we sit down and do this type of multi-dimensional analysis, not only looking at part solutions.
Thank you. Inspiring approach.
Cool. Thank you very much, Dionysios and Klio. That was really, really interesting. Also, thank you to everyone who has attended our first WaterWise Hub webinar. Please do sign up to our next 2 installments to the spring webinar season. I have put the 2 links to the next 2 in the chat. So yeah, please scroll up and have a look. They are 2 weeks from now on the Monday, so that's the 30th of March, and then on the Wednesday of that same week on the 1st of April. Yeah, once again, a big thank you to the two speakers today. There has been a email put in the chat for you, Dionysios, but if anyone else has any questions, I have also put my email in the chat, so feel to email me and I will forward your questions on. Yeah, and I hope to see you again in 2 weeks' time, and have a lovely rest of your afternoon, and thank you for attending. Thank you.
Okay, Elder, I will send you a registration link or maybe a registration password so you can log in. And feel free to ask me the question in an email so we can continue this discussion. Thank you.
Thank you.
Thank you very much. Bye-bye.
Bye.
Bye.
Have a nice day.